Cool. Welcome, everyone. Hi, I hope you have enjoyed Keynote. This is the first session after lunch, so I hope you're not too tired. So today we're going to be talking about LLM ecosystem on Anyscale. My name is Kourosh. I'm an engineering tech lead here at Anyscale, working on LLM, mostly on DevX side of things. I'm sure you got to familiarize yourself with Anyscale from the keynotes, but essentially, to summarize things from the keynote, we have built this general purpose AI platform with on top of Ray that essentially makes distributed computing easier for enterprise use cases. And lately, LLMs are becoming a big part of these kind of like ecosystem. And there's this constant need for like new abstractions, new set of primitives to make these like working and building applications on LLM much easier. So at Anyscale, we built like a suite of tools, libraries, and abstractions to essentially allow LLM developers to kind of like navigate this space much easier and faster. So today I'm going to be covering that. And just to get things started, I'm going to start by like who this talk is really suited for, or most takeaways are for. So if you're like an enterprise with a lot of LLM use cases, or starting to essentially plan that ahead, or engineers building like very generic LLM workflows, or broadly speaking, whoever, like anyone who wants to tap into the power of like open LLMs at a scale, this is like the talk for you. I'm going to talk about like how Anyscale fits your kind of needs. So to give the talk a little bit more structure, I'm going to start by like discussing how we think about closed versus open weight LLMs, and how you should think about strategizing around the developments there. I'm going to talk about LLM dev cycle a little bit, how we kind of offer serving, training, and evaluation solutions around this. And last, I'm going to talk about like Anyscale platform integrations and the roadmap ahead of this thing. So let's start by talking about closed versus open weight LLMs. So if you asked me this question of like how we should think about this a year ago, it was very easy to make an argument in favor of open weight LLMs just because of like cost. Merely considering cost, it was like the right choice because you couldn't go into production with like closed LLMs at the time. So what we've seen in the last, I guess, 18 months, as also Mark pointed out in this fireside chat, is like closed LLMs, especially like this chart is for GPT, but it kind of generalizes around like all of these like API providers, that these like models have got dramatically cheaper. Like it's 100x, more than 100x drop in cost on inference for like almost the same quality of these old, the preceding models. And on the other side of the spectrum, when you look at open weight models, they have also been getting better, especially with like pushes from Meta and on the Llama side. So on both sides, you're seeing like they're addressing the shortcomings they had compared to a year ago. Like closed models are getting much cheaper. Open weight models are getting like much better in quality. So it's really like hard to kind of like, if OpenAI is providing APIs like that are very robust, reliant, and it's like getting cheaper, why should we go and think about self-hosting like our own open models? Like that's a very valid question that is actually getting harder to justify. The way I think about it, like there are two arguments for this, right? The biggest one is obviously security. Like if you're a company or an enterprise, like I know biotech firms are falling into this, like banking companies are falling into this category. Like you have very stringent like requirements around like how your data flows, where your data sits. And for those, I think like self-host, like going with closed, like any essentially API provider is not a really good option. So this is where you essentially have to think about and strategize, okay, what am I going to do? Am I going to go with like, secure enterprise version of these closed models, and those are going to be much more expensive? Or is this like self-hosting them is going to be much cheaper? But this argument kind of doesn't generalize broadly, but like how I think about what generalizes more broadly to everyone is like this argument, depicted in this trade-off space where whenever we are kind of building LLM applications, we are constantly thinking about like, improving like 3 dimensions, essentially thinking about these 3 axes here. So we've got quality, latency and cost. So latency is about like, okay, user experience, what kind of latency profile can I tolerate? Am I streaming output building a chatbot? That has a different requirement than if I want to build an agent. On the cost side, you're like basically reasoning about, okay, what is my traffic going to look like? Is there like a high QPS that I'm kind of foreseeing for this application or not? And that really impacts your cost. And at the same time, quality, obviously. So you want these models to kind of operate well in for the application you're kind of deploying. So with closed models, for quality, you obviously get some knobs to control. It's like prompt engineering or in some cases fine-tuning. But pretty much like latency or cost is dictated after that. So you don't have much control over like how much is going to cost or how fast you're going to kind of output tokens. To get around this, I think like only solution is like, for now at least, taking control over your own stack and deploying language models yourself. And, in open models, you can essentially, like deploy them on like different types of hardwares, or like depending on your workload, you may actually incorporate some sort of speculative decoding or like prefix caching, these levels, like these deep optimizations that could be tied to your own application. And you can essentially decouple these like inherently things like in this interdependency between these three things. And if you want to, unlock yourself from this artificial bound, I think like you should strategize around building primitives to be able to host these models yourself. And that really down the line ends up being cheaper. You can essentially satisfy the quality and even like improve your margins over time as you collect more data. So yeah, let's take a look at what now an LLM dev cycle looks like. So usually people start from serving these models. So for this, we've built RayLLM, which is a serving library that I'm going to talk about. And sometimes this is not enough. Over time, you collect more data. You want to do some sort of refinement. The quality falls short. And for that, we have built this fine-tuning library, LLMForge. It's mostly for post-training kind of operations. And then for eval side, like every time you make like design decisions, such as prompt engineering or like fine-tuning, you want to be able to like scalably like run large-scale evaluations on like large data sets that may represent your problem. And this is not just a one-shot like pipeline that you go through. You always like almost go like form a flywheel out of this. You deploy, you collect more data, you fine-tune either a smaller model or this like improve the quality of the model, and then you do batch evaluation to make sure it is meeting the quality bar. So it's very important to have like a streamlined and like unified ecosystem for dealing with this. And this is what we've built at Anyscale. So we're going to talk about each component individually next. So on the online serving part, we've built RayLLM. So RayLLM is this LLM serving system built on top of RayServe, where you can essentially bring any inference engine, such as VLM or TensorRT, and essentially get an OpenAI compatible service that has production like features built in, like auto scaling, fault tolerance, observability around like things that could go wrong, and recovery events and things like that. So it's very feature rich. The way I categorize like the features is like through these different types of features. So there's like a ton of features around like production readiness, like auto scaling, cluster recovery, being able to like launch and shut down these services using SDK are all like around this production readiness story. There are like functional features, like you can essentially enable activate JSON mode or like function calling on any open models, even if they don't support it like natively. You can do like for when you have a lot of fine-tuned models, you want to deploy one base model with a lot of like loaded adapter at runtime that is multi-LoRa. All of these functionalities are built in here. And there's a lot of like cost reduction features. So we heavily invest in this dimension as well, like things like initializing your model fast. Why does it matter? When you want to like auto scale and you have a dynamic traffic, you want to be able to respond to that traffic by not like actually auto scaling your cluster and not having like a static cluster all the time. Things like prefix caching or like other cost optimizations are built into this framework. So I'm going to show a quick demo of like how it looks like in action. So RayLLM essentially like when you go to an Anyscale console, you go on a workspace that has essentially this like RayLLM installed. RayLLM comes with this interactive CLI where you can essentially run and like configure the model that you want to run or other settings. And then in the end, it's going to generate like a YAML config that describes your service. And essentially, you can essentially deploy this service into Anyscale services. And what Anyscale does is it starts a cluster and loads up the replicas and starts the engine itself and makes the model healthy. And all of this is going to be really like very streamlined, and you're going to get to see like an OpenAI compatible API. So here I'm showing like the API endpoints, the chat completion API, where it's like you have the same arguments that OpenAI has, so you can essentially use this as a drop and replace for where OpenAI is active. Or you can essentially use these UI components that we have built to connect to that service, find your model, and like start doing a vibe check or like prompt engineering, more extensive prompt engineering on this. So this just gives you like a vibe of how this works. There is a more in-depth discussion later on, like conducted by Cody and Phillips, on the actual optimizations that were put into place for doing accelerated LLM inference on Anyscale. I highly recommend to check this out if you're interested in like the optimization around like LLM inference. But for the sake of time, we're not gonna dive deep here. That brings us to the next topic, is like fine-tuning. So LLMForge. LLMForge is this like productionized library that we have on Anyscale, which is essentially some design patterns using Ray Train, and Ray Data, along with other open source libraries like Hugging Face, DeepSpeed, etc., to essentially enable a higher level user experience for fine-tuning and post-training LLMs. Again, lots of features, categorizing them here. Like for example, it supports LoRa, full param. You can bring any Hugging Face model, like it was mentioned today in the keynote. There's like a very flexible control over all hyperparameters that you have, like experiment tracking built in, and a lot of observability around like how training jobs are running. You can do essentially a wide variety of fine-tuning, like types, like tasks. You can do causal language model training, instruction tuning, classification, preference tuning, or even continuous pre-training if you have like large amounts of data and you want to do domain adaptation. And a lot of like performance optimizations are baked in, like gradient checkpointing, mixed precision, like latest CUDA, like flash attention kernels, Liger kernel that are kind of built from the open source. And on top of this, we have a few like proprietary features that I'm going to talk about next. Okay. Oh yeah. And then the API still remains simple, even though there's like a lot of complexity behind the scene. You have like a CLI. You pass in a config YAML where you specify like your model type, the data path, and a bunch of hyperparameters that you want to modify, even if you don't want the defaults, for example. So one thing that sets this LLMForge aside from contenders, I would say, is it gives you very like flexible control over like cluster shape that controls cost and speed of training. So what we hear from a lot of customers is like they don't have access to the latest like GPUs, or it's like usually a busy pool, like a busy queue to kind of get their hands on these type of things. The nice thing about like LLMForge is like it's very flexible. It stays like you don't have to essentially like the same code can run on any sort of cluster and cluster shape. And you can essentially see like and benchmark the trade-offs here. So this plot shows like, for example, the landscape of like changing GPU type from like and cluster shape, going from like one node that has 8 machines on the same node to like 2 nodes that have 4, and then like 8 machines that have individual like GPU cores, and how that plays in like throughput, for example, on different like zero sharding like strategies. So you get maximum control over like benchmarking all of these things and adjusting training pipelines depending on what type of hardware accelerators you have in hand. We've done some proprietary optimizations in some places. I'm going to just mention one prime example here. So for preference optimization or like distillation type of workloads, where The compute paradigm is a little bit different from like traditional supervised fine-tuning. So in this type of like algorithms, you usually have like a model that is acting as a reference model. It produces some sort of logits on the output, and you have like a target model that is using those logits to kind of bootstrap and form its loss based on that. And then you forward back probe on that model. There's tons of like implementations of this out there, but most of them fall into this like non-Ray sort of implementation, where a GPU, a single GPU like machine is kind of time multiplexed between these different compute layers. Like if you want to do forward pass for the reference model, that happens in sequence with the training like the target model, for example. What we've done in like implementations of this like algorithm, we have overlapped these computations. So achieving like a, up to 50% more throughput, for example. And these are only possible when using Ray, where you can essentially independently orchestrate processes and then connect them to each other. Yeah, so another thing to point out on like regarding fine-tuning is like there was this constant need of like continuous fine-tuning. You start usually like with a single data set, seed data set, you fine-tune, you get some, you deploy it, maybe in combination with some other model, and then you collect more data, and you want to repeat this process. So it's very important to be able to load up your weights from their initial condition and continue fine-tuning, and then mix and match these different choices. So we have like a few case studies of like where it's going to be useful, like for continuous supervised fine-tuning. In this blog post, for example, we have shown that like you can essentially excel math reasoning by combining different distributions of data sets related to the task. And if you repeatedly improve, you can essentially see that, okay, I can improve the quality benchmark. This is a kind of an old like study done on like Llama 2, but still holds true. Another more recent one is like in preference tuning, where you don't want to over-optimize your policy so much that it kind of like overfits to your current distribution of like data. So in these cases, you may want to like do iterative, training and then rolling out into real world, collect more data, and then again retrain. And we've shown that, okay, with DPO, with many, like 2 iterations of DPO, you can essentially continuously improve like for a certain niche task. So this paradigm kind of still holds true, and we've enabled, like made it very easy for people to like bring their own initial weights, whether it's like full prime weights or LoRa adapter weights, and start training from those initial checkpoints. Yeah, so that brings us to the next topic, evaluation. So we built something we call like RayLLM batch. It's like, we're still finding good names for it, but for now it's RayLLM batch. Basically, it's a combination of Ray data plus VLM engine. So VLM has this like, built-in kind of differentiating feature that is built for high throughput because of page attention. So it's very useful for like these large scale batch offline jobs. So we use that engine for like building this kind of paradigm here, which basically allows you to continuously run like evaluation on large data sets as you make these design decisions through the pipeline, whether it's like prompt engineering or like fine-tune a new model or like a different paradigm that you try, and you want to see its impact on like the global, like the overall performance. Some key enablements that are differentiators here is like we allow you to run these on spot instances, resulting like in a much cheaper like kind of like overall cost. Mostly because these are offline jobs, and if you can tolerate faults, you can essentially recover from them. It's not like as intensive as like online serving. And obviously fault tolerance is another feature built into this to enable spot instances and like some specific config tuning. So it's very important to like when you have offline batches that has a different like optimization profile compared to online serving, and we are kind of like doing that behind the scene for this type of workloads. And yet the API remains very simple. Basically what you end up doing is like you bring your own class, defining what type of processing you want to do, like what do you want to do with text data, how do you want to format it, and then how do you want to pass it to a language model, and how do you want to post-process it. Maybe you want to do an LM as a judge in the downstream task, etc. So you basically have full control over that logical function, and then you wrap that in like a Ray data set call, like a map batches call, and then provide like some higher level concurrency controls to essentially scale this thing up. And yeah, so API remains very simple and yet like very expressive. Yeah, so again, Cody and Philip are going to talk about it. It was also mentioned in the keynote. Some highlights about this thing is like it's going to be end up being much cheaper than contenders. Like so here we have like Bedrock batch or OpenAI Chat GPT-4o Mini's batch cost profile against like these other Anyscale type of benchmark. So we have like 3 variants like BF16, FP8, and FP8 with prefix caching. And you can go anywhere from like 2x all to 6x based on your preference. This result is just obviously for a small model. It generalizes same way to large models, which Cody and Philip are going to cover. Yeah, so I talked about like 3 kind of, I guess, like big rocks that we have built, primitives that you can essentially use to build LM applications regarding serving, training, and eva. And it's very important to be able to integrate them with your existing workflows. So if you have like an ML ops built out of Airflow or like other, graph management, like kind of like processes, tasks, etc., you want to be able to like launch these things, through those processes. So for this, we have introduced we have integrated with Anyscale SDK, where you can essentially treat fine-tuning or batch inference as a job submission. Like for example here, then I'm showing like I'm submitting a fine-tuning job. I'm waiting for it to finish all through this Anyscale API. I can essentially retrieve my model artifacts produced by these jobs using the job ID. I can construct the service config, write in code, and then submit that or deploy that through code. All done here. So you can essentially build wrappers around it, make it simpler, like to expose it to data scientists however you like, using the SDKs we have here. Other types of external integration. On the serve side, since we are OpenAI compatible, this is mostly like a drop and replace on the client side. So if you're using things like LangChain, like there's tons of like these agentic libraries that are getting built out there to kind of like be able to leverage like prompt engineering, like all this like building RAG stuff like around that. This is going to be a drop in and replace. You don't have to change code or anything like that. On the fine-tuning side, you may have like experiment tracking tools like MLflow or like weight and biases already purchased from like your enterprises, so you can essentially readily bring them in and observe like your training jobs and their progresses and like loss functions, etc. That helps you make design decisions better. And all of these are entirely configurable through your existing CI/CD workflows. Yeah, so that brings us to last slide. So all of these QR codes are like essentially starting points for all of these like tools that I've mentioned, RayLLM, LLMForge, and RayLLM batch. You can start there. It's gonna take you to Anyscale and on the exact like workspace that these are built for. Regarding what's coming, on the serve side, we are continuously working on like reducing cost and latency. Obviously, there's more stuff around like DevX. So depending on your workload, you usually have to essentially search over like the engine arguments to be able to find like the optimal setting that has, I don't know, like the lowest latency or the lowest cost or some objective mixture of objectives you have in mind. We want to like be able to automate that and like build processes around like you define an objective and then we go like optimize and find the best configuration for you. There is another thing for connecting serving to like training where we want to automate more. For example, like if you go to production with this serving deployment, you want to collect more data and you want to do some sort of data curation, find where your LLM is not so like that successful, and you want to like do maybe construct downstream data sets for fine tuning more automatically. On the training side, again, continuous improvement on throughput, make things faster. That's a big thing. There's a lot of excitement around like multimodal models, like especially with the latest Llama releases and like Pixtral from like the Mistral team. And like the quality has really come to the level that people are thinking about like integrating them into their workflows and building things with it. The question is, like, can fine-tuning help there? I think this is something we're going to work on a little bit. And the thing that I'm mostly excited about is like this notion of distillation and doing it automatically. So you can very easily like find like applications that you may build like around large models today, maybe like Llama 3 70B, and then over time as you collect more data, you can essentially distill that model for that task into a smaller variance, and reduce cost or like making it cheaper, essentially making it faster. Yeah, so these are the stuff we're working on. We're hiring. If you're interested in this type of problems, come talk to me. But yeah, that wraps up the talk. Thank you. Now, yeah. Questions? Yeah?
The cost comparison that you did, which LLM was being used behind the scene?
Yeah, so the question was for this plot of the cost profile on batch inference. So this is Llama 3.8b running on L4s, not even like the A100s. FP8, like the variations like BF16, FP8, etc. Cool. Other questions? No? We have about 3 minutes. Okay.
The fast API service you showed with the chat, OpenAI
Yeah.
format, is that fully customizable? It's just you can't have OpenAI or you can use your own? Or is it?
So we built this on our kind of serve side. We don't allow customization from customer side, but we expose APIs that are not compatible, that are newer than API. For example, prefix caching, right? Is something, for example, not supported by OpenAI. We defined like our own type of extra arguments in the body or something where you can pass in to enable those features. So some of these that don't fit the existing paradigm, we kind of like become creative. Like JSON mode, we were ahead, and then OpenAI introduced it, so we have some divergence over there. But like overall, like we build features and then we somehow expose that through that API. Cool. So we can end early, I think. Thanks for coming.